Yes, so thank you all for coming tonight. So as Ariel said, tonight I'll be talking about classical physics as geometry, and in particular, geometrodynamics. So I'll try and keep the talk fairly intuitive and not give too many equations. So hopefully there's something for everyone to take away from the talk. So this is the outline of what I'll be talking about. I'll start off with a brief introduction. Then I want to spend a bit of time talking about the Riemannian, Meissner, and Wheeler already unified field theory. I'll then go on and discuss classical geometrodynamics, and in particular I'll talk about one particular construct in classical geometrodynamics, and that's the geon. And then I'll have a few remarks on the nature of quantum geometrodynamics, and finally I will wrap up with some conclusions. So in this talk I want to discuss how we can represent all of classical physics in terms of purely geometric quantities. And by classical physics I mean source-free Maxwell electromagnetism, classical Einstein gravity, source unquantized charge, and unquantized mass. And what this will enable us to do is to have a purely geometric formulation of classical physics. So usually in physics we think of space-time as an arena, and then we have particles and fields which are independent objects which we add on top of some underlying geometry. However, in this talk I want to present a formulation where all of classical physics can be uniquely derived solely from the geometry. And so in a nutshell, what the goal of the talk will be is to take Einstein gravity with no matter, add to it Maxwell electromagnetism with no charges, and show that the combination of these two areas of physics is a purely geometric construct. And moreover, what I want to do is take this purely geometric construct and work back and show that we can derive the electromagnetic field. And also we'll see that there are geometric interpretations of charge and matter, even though we're looking at charge-free electrodynamics and matter-free Einstein gravity. And this will show that all of these concepts from classical physics are really just manifestations of curved geometry. So let's discuss Einstein gravity and Maxwell electromagnetism. So here I've written down the Einstein field equations. So the right-hand side is the stress-energy tensor. So from electrodynamics, you'll remember that the stress-energy tensor is quadratic in the electromagnetic field strength tensor. That's a physical object. And then the left-hand side gives us the Ricci curvature, which just tells us about the curvature of space-time and the geometry of space-time. So Einstein's equation just relates geometry with a physical object, the stress tensor. Now I'm sure you're all familiar with Maxwell's equations in one form. Here they are. These are the source-free Maxwell equations of electromagnetism, and those just tell you how to compute the electric and magnetic field. So if you're unfamiliar with Einstein equation, let me just spend a couple minutes remarking about it. And there's a very nice quote due to John Archibald Wheeler which explains the intuition behind the Einstein field equations and general relativity as a whole. And the quote goes like this: so matter tells space-time how to curve, and then space-time tells matter how to move. And so what this quote means is, if you have a large planet, for example, a sun, a star, or even a high-intensity source of electromagnetic radiation, that'll curve the geometry around the object. So that's what it means to say matter tells space-time how to curve. Now, if you're given some curved geometry and then you come along with a test particle is a particle with negligible mass and negligible size, such that it doesn't alter the underlying geometry, then that test particle will move along a curved geodesic of the curved space-time manifold. So this quote encapsulates all of general relativity and the Einstein equation. So if you want to understand general relativity and you ever take a class on that topic, just remember this quote and you'll be fine. But what I want to do is I want to look at the converse of Wheeler's statement. I want to say, well, suppose we have a curved space-time geometry. Can we work back and work out what it is that is curving the geometry uniquely? And here I'm only doing it in the context of Einstein-Maxwell theory. So we want to say, given the geometry, can we derive what the electromagnetic field is? And this will give us a geometric unification of electromagnetism along with gravity. But first, let me talk about some previous attempts at unifying gravity along with electromagnetism. So probably the most famous attempt at unifying gravity along with electromagnetism would be the Kaluza-Klein theory, due to Theodore Kaluza and Oscar Klein in the mid to late 1920s. And so essentially what Kaluza and Klein did was they added an extra dimension to space-time. So they made space-time 5 dimensions, they added a 4th spatial dimension, and they compactified this dimension. So the way to understand compactifications is, say you take a large sheet of paper and then you roll it up into a tube, you've compactified one of the dimensions. So this is what they did. And it was very nice. What Kaluza and Klein showed is that if you look at the source-free Einstein equations in 5 dimensions, what you get out is Maxwell electromagnetism along with Einstein gravity plus something called a dilaton. So a dilaton is a scalar particle which represents scalar dilatations of the space-time metric. The problem with this is, in nature, we don't observe light scalars and we don't observe scale invariance. So this was the problem that a lot of people saw in the Kaluza-Klein theory. Why do we have a dilaton in the spectrum? Around the same time, Einstein was looking at his unified field theory. And here he essentially treats both the metric and the connection as fundamental fields. Normally in standard general relativity, you just treat the metric as the fundamental field. Einstein spent 20, 30 years on this, and it was shown around the 1950s that if one looked at the equations of motion using unified field theory, the equations of motion for a charged object behaved that a charged object moved as if it was chargeless. So this is obviously the incorrect physics. So we don't need to go into unified field theory. There's also another attempt at unifying electromagnetism and general relativity, and that was due to Weil. Weil essentially wants to add in some extra vector field which measures the length of a vector. So when you look at a curved manifold, you have a way of measuring the direction of a vector when you do parallel transport. And here Weil essentially introduced a length connection which will tell you the length of the vector. It was actually Einstein who pointed out a flaw in this theory. It led to non-integrability. But if we just summarize all these attempts, you can go on. There's many other attempts at unifying electricity, electromagnetism, and gravity. What they all do is they attempt to add extra structure to 4-dimensional space-time as we know. They add extra physics to Einstein-Maxwell theory. However, what I want to do is I just want to take 4-dimensional space-time, classical Einstein gravity, and Maxwell electromagnetism, and show that they are already unified. That is, we don't need to add any structure to the physics. We can just take the physics we know and love and unify it into a purely geometric form. And this we might call already unified field theory. So let me talk about that for a little bit now. So we want to show that Einstein-Maxwell theory can be written purely in terms of geometry. And to do that, there's 3 conditions that we need to check. So the first condition we need to check is the following. So given that the geometry arises from a solution of the Einstein-Maxwell theory, we need to know what are the necessary conditions on the geometry. So that is, we take the Einstein-Maxwell equations, we combine them into a purely geometric form. That gives us necessary conditions for the geometry. The second condition we need to check is this. Suppose we have these constraints from part 1. Now we need to ask, can we define the electromagnetic field purely in terms of geometry? And we do this in such a way that the electromagnetic field is arbitrary up to a duality of rotation. So let me just explain what I mean by a duality rotation. So you recall Einstein equation tells you about the curvature tensor as a function of the stress tensor. From electrodynamics, you know that the stress tensor is quadratic in the electromagnetic field strength. Therefore, if we're given a geometry, we can only determine the electromagnetic field such that the stress tensor is invariant. So a duality rotation represents any rotation of the electromagnetic field that leaves the stress tensor invariant. So you recall from electrodynamics, one has 2 invariants of the electromagnetic field, E dot B and E squared minus B squared. So if you do a Lorentz rotation, for example, that will leave E dot B and E squared minus B squared invariant, but it'll change the stress tensor. So here a duality rotation is a rotation that changes the electromagnetic field strength. It also changes the electromagnetic invariance, but it will leave the stress tensor unaltered, and therefore by Einstein's equation it leaves the curvature unaltered. So now we come to the third point. Given that we can define an electromagnetic field from the geometry alone, now we need to work back and say, is this a sufficient condition on the geometry? So from part one, we take Einstein-Maxwell theory, we combine it into pure geometry. It's not clear that that geometry is sufficient. So normally what we're really doing here is taking two second-order partial differential equations and combining them into one fourth-order partial differential equation. And it's not clear that all the solutions of this fourth-order PDE are the same as the individual solutions of these two second-order PDEs. But actually, it's been shown by Riemannian back in the mid to late 1920s, 1925 to 27, and also Meissner and Wheeler in 1957, that you can combine Einstein-Maxwell theory into pure geometry. So let me discuss the answers to these questions. So we can look at the answers to these three problems. So the first condition says, what are the necessary constraints on Einstein-Maxwell theory? Here they are. So the first condition says that the trace of the curvature tensor vanishes. So you recall in electrodynamics, the trace of the stress tensor vanishes. And if the trace of the stress tensor vanishes, it follows that the trace of the curvature tensor vanishes. That's what the first equation says. The second one says that energy density must be positive definite, which is obvious when we're considering electromagnetic radiation. And the third equation expresses Einstein-Maxwell theory in a purely geometric equation, and we might call this, say, the Riemannian-Meissner-Wheeler equation. So these are the necessary conditions on the geometry. Now, given that we have defined these necessary conditions on the geometry, we can now say, what is the electromagnetic field strength tensor? We can define it as follows. So here on the right, there is this tensor xi mu nu, which I won't write down, but that is a function purely of the geometry, and it's called the Maxwell square root tensor. So the reason you can intuitively think of it like this. Einstein's equation tells you the curvature tensor is a function of the stress tensor. The stress tensor is quadratic in the electromagnetic field tensor. So if I want to get the electromagnetic field tensor, in some sense, I must take the square root of the curvature tensor. That's roughly what's going on here. And here we have this parameter alpha, which is the duality rotation I mentioned before. So this parameter alpha is a function of space-time. And just for example, when alpha is equal to 0, you have an electric field, and when alpha is pi over 2, you have a magnetic field. And the point about this is when we impose Maxwell's equations on this field strength tensor, then we will get the dynamics for alpha. And what we find when we impose Maxwell's equations on this proposed field strength tensor, we find that the gradient of alpha is a one form. This one form is a function purely of geometry. It's not important. But the point is, you know from electrostatics, when you take the curl of a gradient, it's always 0. The curl of a gradient is always 0. But that's only true when you have a nice, simply connected space. What we'll see later on is that actually the curl of the gradient need not be 0. And this is actually important. So this condition here, that the curl of a gradient is some number, is non-trivial in geometrodynamics. I'll talk about multiply connected topologies later on. And the third condition is, are these geometric constraints from part one, are they sufficient? And they are. In part one, we have these purely geometric equations for Einstein-Maxwell theory. Now we define an electromagnetic field strength in terms of the geometry. Now we impose Maxwell's equations, and when we impose Maxwell's equations, we do not get additional constraints on the geometry. So it's both necessary and sufficient. This is already unified field theory. This is Einstein-Maxwell theory written purely as geometry. So let me just go over the equations again. The first one says the trace of the curvature tensor vanishes because we're working with chargeless electrodynamics. The second equation says that we have positive definite energy density, and the third equation writes the Einstein equation purely as geometry, and this last condition tells us about this duality rotation alpha, and in a simply connected space in here, this integer would be 0. So this here is the unified field theory. So what it does is it represents a purely geometric form of Einstein-Maxwell theory, and it's both necessary and sufficient. So what this means is, in physical terms, the imprint of the electric field on the geometry is so distinct that just by looking at the geometry alone, you know what the electromagnetic field is. So a way to imagine this is, you know that if you have some object in space, it'll deform space around it. Put a little ball in space-time, it will curve it a little bit. But suppose if all you saw was that curvature of space-time, you wouldn't be able to then work back and tell me what that ball was that caused that curvature. But for the electromagnetic field, it's quite different. Just from looking at the curvature of space-time, you can work back and tell me what the electromagnetic field is. That is highly non-trivial. But if Einstein saw these equations, he would probably poke his tongue out and say, you haven't really unified Einstein-Maxwell theory. For one, when you normally unify different areas of physics, you normally write it as a variational condition. So you're used to classical mechanics where you set the variation of the Lagrangian to 0. Here we have not written a variational condition. Moreover, there's a very nice quote by Leopold Infeld, who was one of Einstein's collaborators, and he said that Einstein always felt that looking at the sourced Einstein equation was in bad taste. And that's because the stress tensor is a physical object, and it's a function of space-time. But to know what the points are in space-time, you need to know what the metric is beforehand. But the metric comes from the solution of the Einstein equation. So how do you know what the points are in space-time without knowing what the metric is? So Einstein was a big proponent of looking at the sourceless Einstein equation where you have pure geometry. Here we haven't done that. But as I've said a few times, it's not a given that one has necessary and sufficient conditions to determine the electromagnetic field. So now that we have looked at geometrodynamics, so geometrodynamics is unifying Einstein gravity, Maxwell electromagnetism into pure geometry, we can now give a partial classification of Riemannian geometry. So here I've divided Riemannian geometry into 6 subclasses. They're not mutually exclusive, but they are interesting for physical applications. So the first case might be when the Riemann curvature tensor vanishes. That just means you have flat space. That's not very interesting. The second condition would be where the Ricci tensor vanishes, and that would correspond to a solution of the sourceless Einstein equation, and that's just known as a pure gravitational field. As you might see, for example, when you're looking at the solution of the Einstein equation on the exterior of a planet, for example, in the Schwarzschild metric. And now we come to geometrodynamics. So geometrodynamics is the dynamics of the geometry due to the electromagnetic field. And as we've seen, we can combine Einstein-Maxwell theory into pure geometry. It's given by these 3 expressions. And what we find are there are only 5 components for the metric that are non-trivial. We can also consider various subclasses of geometrodynamics. So suppose this term here in parentheses vanishes. You can actually express this term in parentheses in terms of the electromagnetic field invariance. So you know that the invariants of electrodynamics are E dot B and E squared minus B squared. So if this term in parentheses vanishes, it follows that E dot B is 0 and E equals B. So this is a special case of electromagnetism where we have orthogonal electric and magnetic fields. And you can actually express the Ricci curvature tensor as the product of 2 null vectors, and there's only 3 components of the Ricci curvature tensor. Another interesting case is where the term in parentheses is non-zero, but the duality rotation is a constant. When the duality rotation is a constant, you can always rotate it such that it's 0. And as I said before, when this duality rotation is 0, you just have electromagnetism, a static electric field. We also have the case where the Ricci curvature tensor is arbitrary, and that would just be some unrestricted Riemannian geometry, but of course that has no physical laws. So this is a partial classification of Riemannian geometry. Before I move on to some more physical topics, I wanted to take this time to just talk about one little topic that causes a lot of debate, which I like a lot, and that's the example of the uniform gravitational field. So the question is this: is the uniform gravitational field an example of gravity? Now, according to Chandrasekhar, the 0th law of gravitation states that the requirement for the absence of gravity is that the Riemann curvature tensor vanish. Okay, so let's look at that in the context of the uniform gravitational field. So here I've written the metric for the uniform gravitational field, and you can obviously see the metric is non-Minkowski. Yet if we go and calculate the curvature, we find the curvature is 0. So we have somewhat of a paradox. The metric is non-Minkowski, but the curvature vanishes. So is this really an example of gravity? Well, what we can say is that if the Riemann curvature tensor vanishes, it follows that the metric is non-Minkowski. So if we take the contrapositive of that statement, if the metric is Minkowski, then the Riemann curvature tensor vanishes. So what that means is that the vanishing of the Riemann curvature tensor gives us necessary conditions for the metric to be Minkowski, but it does not give sufficient conditions. So if the if the Riemann curvature tensor is 0, it is not clear that the metric is Minkowski, and this example proves that case. So here we have a case where the Riemann curvature tensor is 0, the metric is non-Minkowski. But the point is, the Riemann curvature tensor is exactly that. It is a tensor. So if it's 0 in one coordinate system, it is 0 in all coordinate systems. Therefore, I can transform this metric and make it Minkowski. So with that in mind, it follows that the uniform gravitational field is not an example of gravity. It really just represents an accelerating coordinate system that can be transformed away. So what we know about gravity is that gravity is represented by tidal forces. That is relative accelerations. Gravity is not represented by absolute accelerations. So here we have no tidal forces. Therefore, this is not an example of gravity. But if you're Einstein back in 1916, you can read his paper and you can read some letters that he wrote to Max von Laue. Einstein says something different. He says, no, gravity is not synonymous with curvature. Gravity should be looked at in regard to the connection. If the connection is non-zero, that's when I know I have gravity. There's also a very nice calculation in the literature by a physicist, Desloge, if you want to go look it up. He asked himself the question, what is the curvature tensor of a uniform gravitational field? He assumes what the form of the acceleration is in a uniform gravitational field, and he finds a non-zero result for the curvature. And he says, well, a uniform gravitational field is therefore an example of gravity. Obviously, his calculation is erroneous, and the error he's done is he's assumed that the acceleration in a uniform gravitational field is constant. It's not. It's a function of position, as you can quite see here clearly from the fact that there's a z in the metric. So let me just summarize what all this means. Some people say that curvature is not synonymous with gravity. Some people say the connection is synonymous with gravity. Some people say it's the metric. But if we summarize this example, we have a modern definition of what we mean by gravity. Curved space-time is the same thing as a non-uniform gravitational field, and flat space-time is the same thing as a uniform gravitational field. So whenever you're talking about gravity, what you're talking about is non-uniform gravity. This here is an example of flat space-time. And you can always, in flat space, go to an accelerating coordinate system. Just go along and jump on a merry-go-round, and you'll be an accelerating coordinate system. But you're still in flat space. So that's not an example of gravity, and neither is this. So I hope that cleared it up for you, and if it didn't, we can talk some more. Now we come to the physics. So there won't be any more equations, I don't think, maybe one or two. But now we come to geometrodynamics, classical geometrodynamics, and the geometric description of classical physics. So here I've written down the classical, the objects in classical physics, their geometric description, and their quantum counterpart. So I'm obviously not going to talk about their quantum counterparts because this is all about classical physics as geometry. So let's consider the first classical object, gravitation. What is the geometrical description of gravitation? Well, my last slide just sort of gave you the proof that gravity is curvature. We can also consider electromagnetism. What is electromagnetism? Well, from already unified field theory, we know that electromagnetism is the same thing as space-time curvature and the rate of change of space-time curvature on the same Riemannian manifold that you have gravity defined on. So we've covered that. All good. Now we want to come to what are unquantized charge and unquantized mass in the context of geometrodynamics. So remember, we have no charge in our space-time. We have no matter. We're looking at charge-free and matter-free Einstein-Maxwell theory. But we want to give geometric descriptions to charge and matter. And what we will see later on, I will show you, unquantized charge can be represented as lines of flux in a multiply connected topology. I'll explain it later on. And unquantized mass can be represented in the form of geons, which are localized distributions of electromagnetic and gravitational radiation. And I will present another example of unquantized mass. The thing to keep in mind about mass and charge is that they are quantum objects. The fact that charge is quantized is a quantum statement. The fact that the E you know and love, 1.6002 10 to the minus 19 coulombs, that's a quantum statement. And you know that mass and charge receive quantum corrections, which can be large or small, if you go on and do quantum mechanics. So here we're looking at unquantized charge and unquantized mass. So let's look at the geon first. This will give us an example of how we get an object which looks like it has mass but really doesn't. So the geon was due to John Wheeler in 1955. And geon stands for gravitational electromagnetic entity. So the G stands for gravity, and the E stands for electromagnetic, and the on is the root word for particle. So you know you have electron, photon, boson, gluon. Now we have geon. And so now I'll explain to you how the geon works. So you know that if you have an electromagnetic disturbance, it has some energy. From Einstein's equation, if we have some energy, we have some mass. E equals mc squared. So now suppose we have a collection of electromagnetic disturbances. That means we have a collection of objects with mass. And then you know from Newton's law of gravity, objects with mass attract each other. So the easiest way to construct a toroidal geon, that's the simplest geon, is picture this. You know that if you have a sun, star, an object, that if you have light in the vicinity of this object, it will bend its path around the object. So now replace that sun or star with another light beam. So picture two light beams, two pencils of electromagnetic radiation, for example, counter-propagating. So two light beams coming towards each other will actually curve one another's space-time such that they now start to follow a closed circular path. They have very high intensity, and they now form this closed circular orbit, and they're held together by the force of gravity. So here a geon is a closed object purely of electromagnetic and gravitational radiation. One way to understand it is this. You know in electrodynamics you've seen waveguides. So a waveguide is electromagnetic radiation confined by a metallic conductor. Suppose you remove the metallic conductor, then you just have electromagnetic radiation. Now suppose the electromagnetic radiation is confined by the force of gravity. That's what a geon is. So a toroidal geon is a toroidal waveguide where the electromagnetic radiation is bound by the force of gravity. Now I'm not saying that electromagnetism or electromagnetic waves have mass, as you know they don't. But we can think of the curvature of space-time as a force of gravity, where the attraction is due to some associated mass energy. Or if you want, you can just say, well, electromagnetic radiation curves space-time. Due to the curvature of space-time, these two light beams will attract. So this geon is just a standing wave. You have electromagnetic radiation just going around in a circle, and it's bound in a circle due to gravitational attraction. So we're doing classical physics, so the only constants we have at our disposal are the speed of light, c, and the gravitational constant. So we can give an estimate for the mass and the major radius of this geon. And so here we have these scaling laws, and then we need to know what is a good estimate for the action. So when you do quantum mechanics, the first thing you learn is, action has units of h bar. So normally a good estimate for action is h bar. But h bar is a quantum constant, and it has no role, or it's invalid to ever put down h bar in a classical theory. So what we need to do to estimate this action, as was pointed out just now, is to do a classical guesstimate for it. And essentially we do just that. We assume that the electric field here in this geon is much, much larger than the electric field one would get when you excite pairs from the vacuum. In any case, what you find is that the action is roughly 90 orders of magnitude larger than h bar. And the mass of the geon is 10 to the 39 grams, and the major radius is 10 to the 11 centimeters. So for comparison, we can compare the mass of the sun and the radius of the sun. We find that the mass of the sun is 6 orders of magnitude less than the geon, and its size is an order of magnitude less than the geon. So the only good news is that the geon can fit in the universe, but it's obviously not a very good model for a classical particle. There's a nice little story. Wheeler was at a conference, and I think it was Peter Bergman asked him a question. Bergman was one of Einstein's collaborators. He asked him, what is all the motivation for looking at these geons? And Wheeler said, well, I mean, obviously they're not a model for classical particles. You can see from this. But he said they represent interesting solutions of coupled nonlinear equations. And he was actually interested in geons for another point of view. When you look at the study of bodies in general relativity, bodies of finite extent, Einstein used to think of a body in general relativity as a singularity in the metric. Here we have a geon which represents a non-singularity in both the metric and the electromagnetic field. So from that point of view, it's a self-consistent solution within the context of general relativity, no singularities in the metric, and we have a body of finite extent, albeit the size of the sun or larger. Very good. This is the next slide. So that was the toroidal geon, and in general we can have linear, spherical, and toroidal geons. The spherical geon would be where the gravitational radiation is spherically symmetric. And one can construct the linear and the toroidal geon from one another, but let's look at the stability issue of the geon. So we know that we have electromagnetic radiation confined by the force of gravity. So far away from the geon, there's no force of gravity, and there's just electromagnetic radiation out at infinity. So we can represent that electromagnetic radiation out at infinity either as incoming radiation, that would be us putting energy into the geon to stabilize it, or that could be energy coming out of the geon, or it could represent an equilibrium of us putting in energy and energy then coming out. So the simplest way, or the most natural thing, is to say, well, suppose the early universe, we had a geon. Then the energy out at infinity represents energy being radiated from the geon. So this means that the geon is an unstable classical body, and it radiates energy out to infinity. And so what you find is its mass and radius decrease with time. And here I've just given one of Wheeler's plots for a couple geon solutions where you have on the left axis the radius in centimeters of the geon and the mass on the right, and the action is in units of h bar. And those little dots on the bottom left are the mass of the proton and the electron. So what you find for a classical geon is that its mass ranges from about 10 to the 39 to 10 to the 52 grams, and its radius is about 10 to the 11 centimeters. So as you know, the mass of the electron and the proton are about 10 to the minus 27 and 10 to the minus 31 for the electron and 10 to the minus 27 kgs. So the mass of a geon is roughly 60 orders of magnitude larger than an electron or a proton. This region here, called terra incognita, is the unknown region where we can't exactly extrapolate the classical geon solutions. But if we summarize what a geon is, it's a classical body in Einstein-Maxwell theory. It's localized. We can give it an effective mass, but at no point can we put our finger down and say there's some mass. It's electromagnetic radiation that is confined. So this is how you get mass without mass in the context of geometrodynamics. You can have particles with mass in a purely geometric setting, albeit they need to be larger than the sun. Okay, let me now go on and say, how can we get charge without charge in geometrodynamics? So the first thing to remember is, here we're not saying that charge and mass are properties of point particles. What we're saying is that charge and mass are properties of the geometry of space-time. So what we can imagine is that on the scales of the Planck length, you have fluctuations in the geometry such that the metric becomes, space-time becomes multiply connected. So what I mean by multiply connected is space-time is connected, but it can have handles or holes in it. And this leads to the idea of wormholes. So the easiest way to understand a wormhole is it's a tunnel connecting two different points in space-time on one space-time manifold. And there's also other ideas that you see around, for example, an Einstein-Rosen bridge, which is a bridge connecting two regions of space-time of two different manifolds. But this example on the right is the simplest wormhole you can consider. So suppose space-time is two-dimensional spatially. And here you have this wormhole. So if you're a little man walking in the vicinity of this hole, you'll just go into one hole and then out the other. But remember, we're considering electromagnetism and general relativity together. So we have electromagnetic radiation propagating in space-time. So if we have electromagnetic radiation going into one hole, it'll go through the tube and then out the other hole. So suppose the lines of flux here went from the left hole into the right hole. A external observer would look at the right hole and he would say, I see charge. He would apply Gauss's law as follows. Suppose you come along with a circle and you draw a circle around the right hole. You then apply Gauss's law. You see lines of electric force entering into your circle. You therefore conclude by Gauss's law that there is some charge in this circle given by the integral of the flux, or the integral of the electric field, which is the flux. The problem is, though, as you know from electrostatics and electrodynamics, when you apply Gauss's law, your Gaussian surface must be a closed surface. When you draw a circle around a hole with a tube going through it, you haven't bounded the region interior to that hole. So Gauss's law, as you've applied it, is not applicable. But if you apply Gauss's law erroneously, you conclude that there is charge in this right hole, and you also conclude that there is an equal and opposite amount of charge in this left hole. So remember, we're doing charge-free electromagnetism, mass-free Einstein gravity, but here we have the appearance of a positive charge and a negative charge at two mouths of a wormhole. So in this context, we do have charge without charge. We can also actually do a back-of-the-envelope calculation for what the charge out of a wormhole mouth is and the mass. And the easiest way to do that is to go and look at quantum geometrodynamics. So let me just talk about quantum geometrodynamics for a minute or two. So in quantum geometrodynamics, we have no constants of nature. Everything is measured in length scales. So for example, the speed of light is a conversion factor between two lengths. The speed of light converts between centimeters and light seconds. Moreover, mass, for example, can be measured in terms of the Schwarzschild radius. So in geometrodynamics, all you have are length scales. There's also no coupling constants. So everything derives from the geometry. So the electric field derives from the curvature, and therefore we have no coupling constants, and that means we have no problems with infinities of coupling constants as well. So the electric field is not an independent object. Everything, as I said before, comes from the geometry. Now, if we go and consider quantum geometrodynamics, you're familiar with how do we get a quantum theory from a classical theory. Feynman has told us how to do this. If I want to consider the probability amplitude for some time evolution from some configuration C1 on some space-time surface sigma 1 into a configuration C2 on space-time surface sigma 2, Feynman tells us sum over all possible histories weighted by this phase factor, which has the classical action in it. So when you sum over all histories, you sum over all possible paths between 2 points, and within that context, you sum over all paths which satisfy the classical equations of motion or do not satisfy the classical equations of motion. The path which satisfies the classical equations of motion becomes dominant in the limit that h bar tends to 0. But in any case, what we see is when we consider quantum geometrodynamics, the natural length scale is the Planck length. And on scales of the Planck length, we find that the fluctuations in the metric are comparable with the elements of the metric itself. And since the electromagnetic field is coupled to the gravitational field in Einstein-Maxwell theory, fluctuations in the metric give fluctuations in the electromagnetic field. And this develops these interesting wormhole behavior I was talking about before. And Wheeler has a nice description of this fluctuations in the metric. He calls it the quantum foam. And this is in his book, which is very nice. You should read it. But this is a picture from his book, which is meant to represent the quantum foam. And essentially what he says is, well, for example, take the ocean. If I'm far away from the ocean looks flat. But near up, the ocean has waves interacting, and I see water spraying everywhere, such that the water becomes disconnected. So picture space-time as an ocean, and near up, space-time metric is becoming warped. If we apply Gauss's law around one of these wormhole mouths, what we find is that the associated charge is roughly an order of magnitude larger than the E, the fundamental constant E. But quantum geometrodynamics, the value of E is unquantized. It can take on any value because you're summing over all possible paths. So in quantum geometrodynamics, you have some charge which can take on any value, and it's an order of magnitude larger than the usual charge if you did give it the fixed value of E. So like I said, this is unquantized charge. You can also work out the mass associated with these wormholes just from working out that you have electromagnetic energy. From electromagnetic energy, E equals mc squared, I have some effective mass. And the mass of these wormhole solutions is roughly 10 to the minus 5 grams. So the point to keep in mind about this theory, we're trying to get objects which have mass and charge. We're trying to take space-time. There's no charges. There's no matter in the theory. But we are warping space-time such that we can have the manifestation of a charge or a mass. Let's look at the properties of such a vacuum of wormholes. We know the mass per wormhole is roughly 10 to the minus 5 grams. Take the mass per wormhole, divide by the volume per wormhole. The volume per wormhole is the Planck length cubed, and you get an effective vacuum mass density, which is 10 to the 93 grams per centimeter cubed. And if you work out what the corresponding mass is in an atomic-sized volume, it's 10 to the 62 grams, which is several orders of magnitude larger than the mass of the universe. But this is the interesting part. Effectively, all this mass is coming from the electromagnetic interactions. So what we've done, the real thing we've done is we've summed over all possible energy modes of this electromagnetic radiation in Einstein-Maxwell theory. Usually what you know in physics, if you have a positive infinity, what you do to the theory is you add a negative infinity. Because the Lagrangian, as people say, is always arbitrary up to a constant I can add. So let me add minus infinity. That happens all the time when one considers QED. But when you have gravity, you can't just add a constant, because gravity is a theory of an inhomogeneous PDE. I can't just add a constant, which would be a function of curvature, when I have the electromagnetic field defining the curvature. So what you find is that when you include gravity, this actually compensates for the divergence of the infinite vacuum energy density. These wormholes have some electromagnetic mass. If they have some electromagnetic mass, they have some gravitational attraction between the two. That represents a bound state, and as you know, bound systems have negative energy density. So we have some negative contribution to the energy density, and we can then give an effective negative gravitational mass. So if you look up wormholes, it's commonly said that to stabilize a wormhole, we need exotic matter. So exotic matter is commonly referred to as matter with negative mass. But it's not really matter with negative mass. It's really just accounting for the fact that we have to include gravitational interactions due to the space-time curvature. Nowhere do we have massive particles with negative mass. But what we find is that when we consider the gravitational attraction between these bodies, it's of the same scale as the infinite electromagnetic energy, and this compensates the infinite vacuum energy. So it's commonly thought that when people do string theory, quantum field theory, that on the Planck scale, if we include the effects of gravity, this will stabilize all the divergences we normally see in field theory. But let me just summarize one part of quantum geometrodynamics. And the ultimate test of any quantum theory, as you know, the most fundamental object in quantum mechanics is spin. And so the question is, how is it that when we quantize a theory with only integrable spins, namely we have the electromagnetic field and we have the gravitational field, how is it that when we quantize such objects we get half integrable spin? There's actually some ways one might try and do this. It's commonly thought that torsion is synonymous with spin. So perhaps if we took a classical theory of gravity and allowed our manifold to have torsion, we might get some classical counterpart of spin. But that's open for debate. Let me wrap up and give you some conclusions. So we've seen that electromagnetism and gravity, Einstein gravity, allow us to have these geon solutions, which are localized forms of electromagnetic radiation. We've also seen that geometrodynamics gives us manifestations of charge and matter, even though we're considering source-free and charge-free electrodynamics. And this shows us that all of classical physics arises from manifestations of interesting curved geometry. So thank you very much.